Okay. Everything we talk about in this report will be stuff we've seen before. But hopefully we'll reinforce and we'll understand a little bit better the second time around. We obviously will not delve into it in as much detail, and some of it you have down pretty solid. Most of you guys can take the derivative of normal stuff or integrate normal stuff. So that stuff we won't really focus on because you guys have that already. So one of the first things we started with at the very beginning of the year was the formal definition of a derivative. And it's good to understand this concept of how it even came about. Where did we decide a derivative came from? So we took a random function. We said, okay, this is a position function. This is some point or object traveling. And we wanted to find the speed of this object at, say, time 2. Actually, let's say time x to make it more general. The only problem is, at the very beginning of the year, we had no idea how are we going to find speed of that. So we had to use our old knowledge. Knowledge-wise from the past, what could we do to find about the speed our point would go in? How do we approximate speed? Okay, close. That's the actual speed, is the tangent line. What did we have even before that?
One of the 2 points.
Okay, the line with the 2 points, the secant line. We said, well, I don't know what to do other than find a line. I've worked with lines a lot. Pretend that's a straight line. Worked with lines a lot. I know how to find speed on a line. What's speed of a line? Slope. What do we know the slope of a line is? That's again taking it further. So yes, slope is derivative. Y minus y is subtracted over x is subtracted. So we had x. We needed something to name this point. We were like, well, we still want it to relate to x. So we decided to name the distance between the 2 points instead of naming the second point something completely different. So usually we call this distance either delta x or h oftentimes happen. So we say this next point is x plus h, which then, if we know any x value, we can always find a y value. How do we find y values? Plug x into the equation. Right now, position is just f of x. So we have f of x here, and f of x plus h here. So this all led us, being able to just label this picture led us to the concept of speed. But right now we're just approximating the speed. So we said the slope would give us the speed. And we said slope is the y values over the x values. So what should our formula look like? Eliana, what should this formula look like?
y minus
With what we've labeled.
x plus h minus x. And then f of x plus h minus f of x.
So that gave us speed, or average velocity. So we had some keywords for this. They could have said average or approximate. And they could have said speed, velocity, or rate of change. Or we could even have given it units. How many meters per second is the particle travel? You could do anything that implies a speed. So that was our approximate speed, our average speed, and then we took it up a notch. Josh and Emma already said, well, this led to derivatives and tangent lines. So we found slope of a tangent line. What did we change about this to make it exact instead of approximate?
You're only using the 1 point instead of.
You're only using the 1 point instead of both. And then we had to have a whole nother way of thinking about things if we were only using 1 point. If we pulled in and we, originally we would have had this and then this and then got closer and closer to the tangent line. How do we pull that point infinitely close? What was our tactic to do that? Derivatives came from this, but there was something even more: limits. Taking the limit of something makes it infinitely small. We did this with differentiating and with integrating. With integrating, we took a whole bunch of areas we wanted to add it together. We wanted to add together. And we made each area's width infinitely small, so we'd have an exact area. Here we're taking this point infinitely close to the other one, so that we're really just using 1 point. So that led to the derivative. Again, I could use the word speed or velocity. I don't have to call it the derivative. If they ask you for the speed or the velocity or the rate of change, they're talking about the derivative. And the formal definition, we know a lot of rules that make things go quicker and easier for us, but the formal definition was the limit as h approaches 0. And the reason we say h approaching 0 is we wanted that distance between the x and the x plus h to get infinitely small. We want it to be 0. Oh, and we can cancel the x's out on the bottom and just have h. So again, this formal definition of the derivative isn't a major portion. Knowing the average velocity formula, that's a major portion. That's something you should just know. If they ask me average velocity, I'm doing y2 minus y1 over x2 minus x1. You're going to ask that on at least one free response. Probably you'll see it 2 to 4 times. Just an approximation. This you'll probably only see one kind of question on, but it's the details where we get those extra points, where we go from a 3 to a 5. So here's our first example. Oh, I forgot I left a place for average versus instantaneous. We won't need that since we already talked about it. So a question like this, they will ask questions on just limits, and so that's where our mindset will be. We'll be like, limit, what tactics do I have to solve limits? Can I plug in the value? Can I do L'Hopital's rule? What can I do? I wonder if you could do L'Hopital's rule. I think you could. What would happen if we plugged in infinity? Sine of, well, I guess sine of infinity. Sine of infinity? Sine of infinity bounces back and forth between positive 1 and negative 1. So, actually L'Hopital's rule wouldn't apply here. we could maybe do like direct comparison, but we couldn't do L'Hopital's rule. Sine of infinity, we have to actually be approaching something. This one, I never actually approach anything. So yeah, L'Hopital's rule is out, which, especially where it's infinity, that's probably what we try first. Plug in infinity, see if L'Hopital's rule would work. So we've got to recognize this format. We've got to recognize, hey, that's how you guys were saying 0, wasn't it? Sorry, I just typed that in incorrectly. So now let's see if L'Hopital's rule would work. What does sine of pi have? Sine of pi has cosine sine.
And cosine.
No, cosine of pi half is 1.
0.
Sine perhaps. Cosine.
Or, sorry, sine of pi halves is 1. Unit circle. We're looking at this point here. This point is 0, 1.
And sine as well.
And it goes cosine sine. So you do have to be careful. Be careful with your unit circle. So if we plug in 0, we get 1 minus 1 over 0, which is 0 over 0. L'Hopital's rule does apply. So we could just do L'Hopital's rule. I'm not sure if that's the same in every case, but that's probably where your mind will go first. So we could apply L'Hopital rule, which tells us to do what?
Take
Take the derivative of the top and of the bottom. H is our variable because H is approaching 0. So we'd have derivative of the outside evaluated at the inside times the derivative of the inside. What's the derivative of the inside? 1 all over 1. We're still doing limit as H approaches 0. Now what happens when we plug in 0? Comes out as,
0.
oh. What did I screw up on that? Or no, that's times 1, not minus 1. Never mind. I thought I wrote minus 1. It just comes out as 0 over 1, so it just comes out as 0. So you could apply L'Hopital's rule, just in case we couldn't. What is this really telling us to find anyway? What part is our actual function?
The sine pi halves.
Sine. The pi halves actually tell us something different. Sine of x is our function. Pi halves is where we want to, where we want to evaluate at. So we would take the derivative of sine, which is cosine, and evaluate it at pi halves, which is still 0. Let's get that one. So we really have two options here. Both are about the same speed. We also want to be concerned with how fast can we get these problems done. I'd never thought to use L'Hopital's rule before on this though, because I was so used to teaching AB and we didn't teach L'Hopital's rule. But I think L'Hopital's rule will work for any of these, which would make it faster. Because the whole problem is that you get 0 on top and 0 on bottom, and you can't divide by 0. So, yeah, L'Hopital's rule should be the faster method. So also with differentiation, we've talked about implicit differentiation, which we used in related rates, which is just word problems involving implicit differentiation, and the physics of differentiation. So implicit differentiation, why do we ever use it? What's the purpose?
So we can derive when we can't get y alone.
Okay. Derive when we can't get y alone. there's a second purpose as well. We sometimes want to implicitly differentiate, I don't know why I cannot say that word very well, implicitly differentiate when we want to take the derivative with respect to a variable that's not in the equation. A lot of times, what do we want to differentiate with respect to? What do we want to figure out a rate of? Over time. A lot of the time, we want to do like dx dt. We want to know what's going on over time. But often, our equations aren't even in terms of time. So our secondary goal is to differentiate let's take this equation and differentiate it. So again, on this one, I cannot get y alone whatsoever. I could try and I would just fail. I could maybe clean it up a bit so it's not as hard to differentiate. What could we kind of do to maybe not make this as hard to differentiate?
Could we multiply by y squared minus 5y?
Usually, we want to get rid of fractions. So if we multiply by y squared minus 5y, we get to do product rule instead of quotient rule. It can actually even be a little trickier than that. What's one last thing that can save me even more trouble?
Cross out x.
Get rid of one of the x's. If we divide both sides by x, then we would just have x squared equals, and I'm going to distribute that to 2y squared minus 10y. So you don't have to do that. We could have left the problem like it was originally. It makes it easier on ourselves. So now let's differentiate. Unless I specify a variable, then we would assume differentiate with respect to x. So my first piece, x squared, I would just differentiate normally. Derivative of x squared with respect to x is just 2x. Power rule. The other part, now we have to implicitly differentiate. We differentiate this piece normally. What's the derivative of 2y squared without worrying about implicitly differentiating? For y. But what do we have to multiply by? Y prime. Now when it's been with respect to x, we've been writing y prime. What if I took this same one, and it would change the first part as well, and I said do with respect to time. Now, since we have a little more direct instruction, we would need to write dy dt. Y prime is not explicit enough. It doesn't tell us what we're taking the derivative with respect to if it's something other than x. So we would have to write dy dt. Then we take the derivative of our next piece. Again, we just do it normally at first. Derivative of 10y is 10. But then we also multiply by y prime. And then usually, if this is asked on like a free response, they say find the derivative, which means we need to isolate y prime. If we don't, it's not going to get you full points. And if it's on multiple choice, they would have done that anyway, so you'd have to isolate y prime anyway so you could see which one matched. So at this point, almost always we have to do one certain step. What do we almost always have to do to get y prime alone? Factor. If there's ever more than one y prime, we've got to factor it out. And then getting y prime completely alone, it's pretty easy after that. And then it's just down to algebra, which we do for our last step. Just divide. So I could ask you a lot of questions with this. I could say, what is the derivative? I could say, what is the derivative at a certain point? You could say at 2, 5, or I could even just say when x equals 2, and I'd have to go back and solve for y, or when y equals 5, and I'd have to go back and solve for x. I could make you find a tangent line. Could make you find a normal line. That one we didn't do nearly as often. Again, it doesn't come up very much. You may or may not see it. You definitely see tangent line. Maybe normal line. What was the difference between normal and tangent line? Anyone remember? It's been a while. It's like first 3 weeks of school or 4 weeks of school. Tangent,
90 degrees.
normal was 90 degrees, so it was,
Oh, so it's a perpendicular.
yeah, it's a fancy term for perpendicular to the tangent line. So over here, if I were to keep differentiating with respect to time, the right side didn't change. What would change about my left side? You'd have to take 2x times dx dt. Now this time I don't really need to isolate because dy dt and dx dt are different. So I can't isolate one over the other unless they ask me to. I could find the speed of x over time compared to the speed of y. And again, this would be applied to something, so let's say, what's a good one? Usually it involves like a person walking, and they want to know the distance from me to the wall, and maybe so the distance from me to the wall in the front, the distance from me to the wall on the side, so if I'm walking like diagonally. So then I want to know one or the other speeds. What's my speed just one direction, and what's my speed the other direction? So we need more information on this one. And then we talked about the physics of differentiation. This one we've seen a lot. Did you win?
Nope.
Sad. Did they at least give you like a cookie or something for doing that?
Sure.
Okay,
And Chick-fil-A.
I was gonna say that's not nearly exciting as a cookie, but they gave you food, so we're good.
Is this mine?
My friend made
Yes.
breakfast for-
Are they both mine?
Those are
Yeah,
both
they're
yours.
yours.
Are you sure?
That's our homework for tonight, all of it.
I was gonna be like,
It's okay.
no.
Oh, okay.
No,
We will have more homework, but it will not be the entire pack.
No, I think they're being too generous there. You can keep some.
Well, I'm not doing that. Okay.
Like, I
give up. Never mind. Okay. So, physics of differentiation. And the physics really works so much with integration. We'll probably talk about it again with integration and put it all together. But with differentiation, we normally started with position, which is either x of t or s of t. I almost always use x of t, but occasionally they use s of t to mean position. Now when we say position, it doesn't have to be like an actual physical position. It doesn't have to be 10 meters from the wall or 15 meters from the water. Position can talk about any word problem where you've collected data and it's not a rate of change, it's just how many barrels do you have or how many people do you have.
Hi.
She's alive.
Sorry if you wrote a success thing. It was
Okay.
awful long.
She was there.
Oh, yeah.
I saw her.
I got lost running into the freeway.
Oh.
Some unit better.
Hard to find that freeway.
So position is an amount of something.
Nope. They had to go to this like side courtyard place. And they're like, everyone's out there. There's like 5 people. Like everyone's in who?
So Ben, what happened when we took the derivative of position?
Oh shit. Acceleration?
Close. Too
Velocity.
Velocity. Okay. Velocity was the derivative of position.
Just took it too far.
And it's represented by a speed or a rate. Meters per second, or barrels per hour, or
Miles
people
per
per
minute.
minute, miles per minute.
I said mice, but
Oh,
that's
mice per minute. That also works. And then we had one more.
There's a lot of chicken in that.
Wait, Melinda, I haven't asked specifically. Melinda, what's the derivative of velocity?
Is that acceleration?
Acceleration.
The one for
That's right.
He's hard up. Thanks, Josh.
I was trying to help Ben out.
Wow,
Oh.
be rude to me. Wow.